It's a wet and windy day in July of 1908. A Dutch experimental physicist named Heike Kamerlingh Onnes and his team in Leiden had just liquefied helium for the first time, reaching temperatures just a few degrees above absolute zero. This milestone achievement made by that team in the Netherlands instantly turned his lab into the spot where you could study almost anything in conditions that no other place on Earth could reach. Onnes was proud of his work indeed, but was far from satisfied. He had a clear but unresolved question lurking in his mind. As you cool a pure metal toward absolute zero, what happens to its electrical resistance? Many had speculated what would happen in theory, but no one had been able to reach conditions in which they could experiment with such a question. With liquid helium available, Onnes could finally measure the resistance of a metal wire directly in this new temperature range, reaching even closer to absolute zero. And so, he began a new mission, to chart a clean resistance versus temperature curve and see which theoretical idea matched reality. However, when the time came to push a thin mercury wire into this helium bath and watch how it behaved under these extreme conditions, what he found didn't look like a smooth curve at all. What Onnes found instead forced him to change how he saw temperature and resistance entirely and to introduce an entirely new concept into the world of physics. Towards the end of the 19th century, everyone agreed on one basic observation. If you cool the metal, its electrical resistivity goes down. But when it came to pushing that trend to its limits, many physicists diverged with their ideas. Three influential views existed at the time, each challenging the other's mindset. The first view was spearheaded by the one and only Lord Kelvin, the man who discovered absolute zero himself. Proposing his idea in 1902, and also without the day's idea of a crystal lattice, Kelvin pictured metals as basically just groups of positive matter with electrons moving through it. He argued, however, that at very low temperatures, metals should stiffen electrically. The roaming electrons would effectively stop moving and freeze to the positively charged matter in the metal. These stiff electrons would therefore imply that resistance would actually stop falling and instead rise again, trending towards infinity as you approached absolute zero. Kelvin was essentially predicting that a metal cooled to a low enough temperature would end up acting more like an insulator rather than a conductor. The second view, held by Scottish chemist and physicist James Dewar, expected the opposite trend. He and his collaborator, John Ambrose Fleming, had previously measured a series of metals at temperatures at around that of liquid oxygen. Though this was not as low a temperature as that of liquid helium, it was still important for collecting such data on pure metals and alloys. From their data, they found that resistivity did not merely decrease linearly, but rather curved downwards in a way that suggested an intersection at zero resistance at absolute zero. Their data also matched Paul Druda's model of metals proposed in 1900, 5 years after Dewar and Fleming's 3-year-long slew of experiments. This model stated that resistance mostly comes from electrons jiggling around and bumping into atoms. If this were true, then cooling should just reduce that jiggling motion and allow electrons to flow more slowly in a straight path, reducing collisions with atoms. In that picture, resistivity ought to keep sliding downward as temperature drops, and in an ideal, perfectly pure metal, it might in principle get arbitrarily close to zero. Of course, actually reaching absolute zero was and still is considered impossible, but that trend of resistivity reducing further and further was the vital part of the theory. The third and final major viewpoint was more cautious than the previous two and served sort of as a middle ground position that was based on experiments at higher temperatures. British physicist Augustus Matthiessen had shown that impurities and defects contribute a temperature-independent part of the resistance. Extrapolating that idea, he and other fellow supporters expected the resistivity of a real metal to level off at a finite value at low temperatures. It was with these three dominant theories on the table that Onnes comes into play. His instincts and the simple Druda model of metals put him closer on the spectrum to the resistance keeps decreasing side. He expected a smooth curve heading downward as the metal cooled, which would eventually lead to an intersection of zero resistivity and zero temperature. Once he had the technology to do so, his immediate reaction was to put the debate to rest and finally determine which of the three theories was correct. To his and everyone's surprise, though, the correct theory was actually none of the three. By 1908, Onnes's lab had been dubbed the coldest place on Earth and allowed him to cool samples down to around 4 Kelvin. At the same time, his group had spent years developing reliable, low-temperature thermometers and measurement techniques, so they had state-of-the-art devices for both accurate temperature readings and electrical measurements. On top of settling the debate of the three theories, Onnes also wanted accurate resistance thermometers for cryogenic work. Pieces of metal whose resistance as a function of temperature could serve as a built-in resistance thermometer scale. To make that work, he needed clean, reproducible resistance versus temperature curves that extended all the way down into the liquid helium region of temperature. To set up his experiment, the first key step was choosing the right material. Onnes settled on mercury for his first detailed study because it could be purified very effectively by repeated distillation. By filling thin glass capillaries with purified mercury and then solidifying them, his team could create narrow wires whose resistance was dominated by the metal itself, not by impurities or defects. He planned to compare mercury with other metals like tin and lead later, but mercury was the cleanest starting point. The wire was mounted inside a cryostat so that it could be immersed in liquid helium and then slowly warmed while the surrounding helium boiled away. The cryostat itself was obviously state-of-the-art for the time. The apparatus consisted of multiple double-walled containers with an area in between the walls that was vacuum-sealed for insulation. Insulating materials were poured into the containers to keep the cryostat at a chilling temperature. The outermost container, labeled in purple, was filled with alcohol to prevent frosting caused by the inner layers and to also keep visibility high. The alcohol container was followed by the liquid air container, labeled in blue, and then the liquid hydrogen container, labeled in green. After the containers were filled with these substances, cooled from separate liquefiers, the helium was transferred from the helium liquefier to the measurement cryostat. By the time Onnes was ready to start testing mercury, the cryostat was capable of reaching temperatures as low as 1.1 Kelvin. Onnes' chief of staff, Gerrit Flimm, was in charge of watching over the cryostat, assisted by another lab engineer, Cornelius Dorsman. Temperature was tracked with a separate gas thermometer, which Onnes trusted from his years of refining gas-based temperature scales. Electrical resistance was measured in a Wheatstone bridge circuit with a sensitive mirror galvanometer in an adjacent room by another lab assistant named Gilles Holst. The bridge compared the resistance of mercury to other known resistances, while the galvanometer indicated the value through means of a light beam deflected by a mirror. This electrical machine allowed the team to detect even the smallest changes as they adjusted the temperature. Holst would essentially watch the beam of light from the galvanometer and yell the reported resistance through a tube that connected the two rooms. The basic experimental plan was quite straightforward. Cool the mercury wire into the helium bath, then record its resistance as the temperature gradually increases. Then, they could build a detailed curve of resistance versus temperature. And 3 years after his first liquefaction of helium, Onnes and his team were primed for their next big breakthrough. On April 8, 1911, Onnes' team in Leiden ran what, on paper, looked like a routine test of their helium setup. The primary goal that day was actually to check that the liquid helium could be transferred reliably to the apparatus and that the measurement scheme worked at these new temperatures. But with the equipment in place, it was natural to also record how the resistance of the mercury behaved as the sample sat in and then warmed out of the helium bath. In their first run, as they cooled the mercury with the liquid helium, they actually did not record the change in resistance of the mercury. They didn't start tracking it, in fact, until it was already fully cooled, in which upon measurement, the resistance was practically zero. Onnes and his team then measured the resistance of the mercury as they slowly warmed it back up. As the temperature of the helium reservoir rose toward roughly 4 Kelvin, the measured resistance of the mercury, to everyone's surprise, shot up abruptly to about 0.1 ohms. If the resistance suddenly vanished, their immediate train of thought was to worry about a short circuit or a loose connection. Onnes, Flimm, Holst, and Dorsman systematically checked the wiring in the bridge. An account of the event was made by a researcher in the lab, Jacobus de Nobel, in 1931 after hearing the story from Flimm himself. De Nobel's account goes as follows. Repeated trials all indicated zero resistance at the liquid helium temperatures. The workers assumed that some kind of short circuit was responsible and replaced the U-tube with a W-shaped tube with electrodes at both ends and at the kinks, presenting 4 different segments for measurement. Again, the resistance was zero, and no short circuits could be found in any of the segments. They continued to repeat the experiment. A student from the instrument maker's school was charged with watching the readings of a pressure meter connected to the apparatus. The helium vapor pressure in the cryostat needed to be slightly lower than the atmospheric pressure so that the air would rush into any leaks, freeze, and seal them. During one experimental run, the youngster nodded off. The pressure slowly rose, as did the temperature. As it passed near to 4.2 kelvins, Holst saw the galvanometer readings suddenly jump as resistance appeared. In their repeated experiments, the team started tracking the resistance of the mercury as it both cooled and warmed. Through their series of tests, the repeating pattern became quite clear. At around 4.2 Kelvin, plus or minus 0.1 Kelvin, the resistance jumped from about 0.1 ohms to an essentially unmeasurably small amount, and back up to its normal value around 0.1 ohms when warming up to the same temperature. The behavior of mercury from this series of tests painted a picture that didn't fit any of the theoretical low-temperature scenarios. In his lab notes, recorded in 1911, Onnes wrote that the temperature measurement was successful, the resistivity of mercury practically zero. He later published his findings in November of 1911 in a paper titled On the Sudden Change in the Rate at Which the Resistance of Mercury Disappears. In describing this behavior, Onnes initially chose to use the language passed on to a new state, rather than coining the phenomenon specifically. After this publication on mercury, he moved on to tests with tin and lead, and found that similar characteristics happen in these metals as well. So perhaps this is a universal phenomenon with all metals once they get cold enough. A couple years later, in 1913, Onnes won the Nobel Prize in Physics for being the first to liquefy helium, and delivered his Nobel lecture in Stockholm, Sweden on December 11, 1913. In his lecture titled Investigations into the Properties of Substances at Low Temperatures, he coined the now famous term. Thus, the mercury at 4.2 Kelvin has entered a new state, which, owing to its particular electrical properties, can be called the state of superconductivity. Onnes and his team continued research on the phenomenon even after this, and in 1914 reached another breakthrough. The team had placed a coil of lead into the cryostat and cooled it down to that critical temperature. Then they induced a current in the lead coil by means of an external magnetic field. With no resistance in the lead coil, the current induced never faded, persisting indefinitely at the team's discretion. As great as this feat was, Onnes also learned very quickly that it was extremely delicate. As it turns out, the superconductivity of the lead coil was quite sensitive to the magnetic field. At a certain strength of the magnetic field, the current reached a sufficient strength that the superconductivity of the lead coil was lost entirely. This obstacle, which stunted Onnes' experimental growth with the phenomenon, wouldn't be overcome for another 50 years, far after his death in 1926. Among low-temperature physicists, the discovery made by Onnes and his team was taken seriously almost immediately. Onnes already had a strong reputation from his work with helium, and no other lab could yet reach the same temperatures to challenge his data. Rather than open rejection, the initial reaction was actually a mix of acceptance and puzzlement. Austrian theoretical physicist and renowned professor Paul Ehrenfest sums up the reaction to this discovery quite well in his letter to Nobel Prize-winning physicist Hendrik Lorentz. It is uncanny to see the influence of these permanent currents on a magnetic needle. You can feel almost tangibly how the ring of electrons in the wire turns around, slowly and without friction. It is also remarkable how none of the existing electron theories of the time could explain a nearly discontinuous drop to zero resistance at a certain temperature. It's also worth noting that Onnes himself could not explain the why behind this phenomenon, but rather only could show the results of the experiment. Over the course of years, as more superconducting metals were identified, the phenomenon became a central problem in condensed matter physics. An explanation for it didn't come until 1957, when the physicists John Bardeen, Leon Cooper, and John Robert Schrieffer published the BCS theory, an abbreviation of their last names, to describe superconductivity. According to their theory, at this critical temperature, the energy of the electrons and ions in the metal itself is so low that the electromagnetic attraction between them becomes the dominant factor. A passing electron attracts ions in the metal, which in turn attract another electron, effectively binding these two electrons into what is called a Cooper pair. Cooper pairs form all throughout the metal, and these pairs behave quite differently from a solo electron. The pairs do not have to obey the Pauli exclusion principle, even though the single electrons that compose the pairs still do. Due to this characteristic, all pairs can condense into a single collective quantum ground state. This creates one large synchronized flow of Cooper pairs that have the same phase and velocity. At extremely low temperatures, the energy required to break this synchronization is simply not there, and therefore you have superconductivity. Today, superconductivity underpins technologies that need very strong, very stable magnetic fields with essentially no energy loss. Examples include MRI scanners in hospitals, NMR spectrometers, and huge magnets that steer particle beams and accelerators. Looking ahead, superconducting cables and devices could enable far more efficient power grids, compact high-power motors and generators, maglev transport, and even help make fusion reactors and other clean energy systems practical at scale. Onnes' discovery of superconductivity was one of the most important, if not the most important, scientific achievement of his lifetime. His lab in Leiden well outlived him and went on to map out superconductivity in several elements, and also to explore its practical possibilities. And all of that started with a simple question about how resistance behaves near absolute zero. A question that was answered with a thin mercury wire, a bath of liquid helium, and the willingness to trust the measurements and accept a bold new idea. If you enjoyed this video, please consider liking and subscribing. Click here if you want to see more scientific progress made during this time period. Thank you for watching, and I will see you in the next video.